this example that we did last time, and then, but let's see, business. So you're not coming here on Friday. The exam is Friday. You're coming to Art 220. Art 220, sometime between 9 and 10, you're going to arrive, and then you'll have 90 minutes to do the exam. So people who arrive closer to 10, I'll be collecting your exams at 11:30. If you replied to my email about the conflicts rescheduling, I have emailed everyone back, and so please check your email and make sure that we've worked that out, your alternative time to take the exam. If you didn't respond to that email and you can't make 90 minutes work on Friday, then you need to email me soon, today, okay, so we can work something out. Let's see. So I think you can bring a graphing calculator. Yeah, you can bring a graphing calculator, just not a calculator that does symbolic algebra. So any basic calculator, basic graphing calculator will be fine. What else? It's some multiple choice and it's mostly multiple choice, some free response. Okay, but it definitely will assess your understanding of things that we're emphasizing, not just your ability to solve problems. Okay, certainly yes, solving problems is really important, but all these ideas that we're emphasizing in lecture it's all on there. Okay, so you have to be ready. And so what does it cover? It covers the basics of rate or accumulation from rate. That was that first week, accumulation from rate. Let's write this down here. And that was basically kind of deriving what the integral is all about, right? Integral as net accumulation, and then we can get a total accumulation function from that. And then we applied that to signed area. We also talked about area, the difference between signed area and area. On the exam, in order to highlight the difference even more, area is called unsigned area. So when you see unsigned area, all that simply means is what we have to this point been calling area. Okay? Is it okay? So unsigned area is synonymous or the same as just area. And what is the quality about area that's important? Area is always positive. It's always just how much space. And how much space is always going to be positive. We know that if we're using integral, just straight up integral, when the function is negative, right, we're gonna carve out areas that are gonna have a negative contribution to the integral. That's why we talked about signed area, right? Signed area. Okay, but if we just want area, then we have to finagle that integral situation to make it always positive. So we just get amount of space, right? Amount of two-dimensional space. And then we've spent a lot of time on volume. And then today we're going to start arc length. And so this is the major emphasis, just a little bit on that. Okay. A lot on 1 through 3, a little on number 4. Yes, please.
Is the test multiple choice or long answer?
It's mostly multiple choice, a little bit of free response. But it will definitely assess the ideas that we're working on, not just solving problems, getting numerical answers. You got to know your stuff. Whatever test, whatever format of test you think is the most difficult, study like it's that. Okay? So if you think, oh, multiple choice, I can ease off. No, you don't know. If you haven't taken one of my tests before, you don't understand. It will test your understanding, even though it's multiple choice. You got to know your stuff. Yes, please.
Do we need to bring in our own scratch paper?
No, don't need your own scratch paper. Other questions? All right, again, Art 220, show up between 9 and 10 a.m. Friday. And expect, so we're just leave. You may get done in quicker than 90 minutes, but I just want to allow 90 minutes for the exam, just so you have enough time to think. Any other questions? Yes, please.
Will you give us the scantrons?
Yes, I will provide scantrons. Have a pencil. You need an actual pencil. Not pen won't work on Scantron. You need a pencil. Bring a pencil. Okay. So this, we worked on this one, right? We were taking this region here, and we said it was the region bounded by x equals 2, y equals 4, and this was 1 something x squared, 1/4 x squared plus 2. And we revolved it about the line y equals 1. Right? We revolved it about the line y equals 1. And so we did it with delta x intervals and delta y intervals, right? So forming the empty shell, once you form the empty shell, then we have kind of two possibilities to fill up that shell and track the volume. So we did delta x intervals first. And so what kind of cylinders, what do the cylinders look like when we do delta x intervals? What do the cylinders look like when we do delta x intervals? Can you imagine? So as you found out when you came to the homework and when you come to the exam, you don't have these beautiful animations that we started off with, right? And hopefully, so go back and watch the videos so to help you conceptualize that. But then you got to get to a point yourself where you can conceptualize that without the real pretty animation, right? So with delta x intervals, a typical... So a typical, I'll draw it over the side here. Let's do a lighter color. Okay, so then a typical, you should be thinking that a typical cylinder looks like this. Okay, and then what? It has a hole because of this right here. Okay. So these are what our cylinders are going to look like. And for delta x, and so we said we came up with a function for those. We came up with the rate of change because the rate of change was what in this case? The rate of change, is it 2 pi rh or area of the base? Area of the base. The height is growing, right? In the current interval, the height's growing, but the radius is not. So this would be area of the base. And we came up with a rate function for that. And then we did delta y intervals. And you should be able to imagine what a typical cylinder would look like if we made cylinders through delta y intervals, right? So in a typical delta y interval, it would be like this. And so then we would get something like this. Right, and that's a sleeve, right? That's hollow inside, totally hollow. And so then each new cylinder is wrapped around the one before, right? It grows in, how does it grow? By its radius, right? Each new cylinder grows by its radius. Height stays the same. And then the next one is wrapped around that one. So these are like sleeves that are all wrapped around each other, right? But the radius grows, and so we know our rate function was 2 pi rh. So I've written down the... I got those volume functions. So this is what we came up for the rate on the first one with delta x intervals, and then the rate on the second one with delta y intervals. That should be consistent with what we had last time. And so how would we get the volume of the whole solid then? How would we get the volume of the whole solid? So this is the point 2, 3. This is the point 4, 6. And this was 2, 6. How do we represent the volume of the whole solid? Tell the person next to you. Well, I want to represent what the volume of the whole, right? The whole solid, this is this thing here. Okay, let's spin the wheel. Here we go. Where's Anley? What'd you say? How do you want to? I want to express the volume of the whole thing. Add them together. We add them together. Let's see. How about Zach? Where's Zach Wright? Oh, right next to him.
Yes.
What do you think? Agree with that?
Yes.
Add them together. Kylan.
Well, you can take either of the functions.
Okay.
And you just have to restrict the domain. So if it was for volume of x, based on the x intervals, it would be the integral from 2 to, what, 6? No, 4, sorry. And then for the change in y intervals, y, it would be 3 to 6.
So she wants to take this integral and say 2 to 4. And do this integral from 2 to 4. Will that give the volume? Yes. Or take this integral and go from 3 to 6. All right? So I don't want to write all that out. Is there another way I can do it without writing all that stuff out? 2 to 4, blah, 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 blah. V1 of 4, right? The whole volume is V1 of 4. You should, that's so if you didn't talk about that when you talk to the person next to you, that's the important thing, that you understand that V1 of 4 represents the volume of the whole thing. Or, what else? V2 of 6. Why? Because we're saying, so these accumulation functions, right, they track the volume as that shell is being filled up with these cylinders. So when we get all the way filled up, so to get it all the way filled up, we want to set x equal to 4, meaning the whole accumulation of those cylinders all the way up to 4, and then we've reached the actual volume. Likewise, with the y cylinders, this function will track the volume. We'll keep track of how much volume you have as y increases. So to get all the volume of that whole shell, you're going to take the volume when y equals 6. That'll be all the accumulated volume starting from 3, y equals 3, up to 6. Okay, so I want to write an expression that I know for sure is half the volume. So tell the person next to you, write an expression that would be half of the total volume of the filled shell. Go. What expression? We want to know for sure what it is. Okay. Where's Shelby? Shelby, yes. V1 over 4. V1 of 4 over 2. Oh, so first of all, I'm going to show you that. When I do V1 of 4 and V2 of 6, what happens? That's what we would expect, right? So this is the volume of the whole thing. So if I want half of the volume, she's saying V1 this over 2. Agree? Wow, something's not happy here. Copy and paste. Not working. Nothing's working. I can't do it. I can't copy and paste, and I can't do Control L. All right, I'll just have to see if this one will divide by for you. Oh, there we go. Okay. All right, so there's half of the volume. And I need to write new ones here. Okay, so what if I go, so this was going from what? From x going from 2 to 4. And y goes from 3 to 6 in order to fill up that shell, right? So I want to ask about V1 of 3 and V2 of 4.5. V1 of 3 and V2 of 4.5. Will those equal half of the volume or something else? All right, so talk about it. So if you think something else, be more specific than just something else. So will they equal half the volume? Going halfway across an x, halfway across an y, or something else? Omar, you're up. Tell me about V1 of 3. Do you think that's going to be, V1 of 3 is when I let x go halfway across. When I let x go halfway across, am I going to get half the volume? So, can you be more specific? You say no. Okay, so it's not symmetric. So can you be more specific than just that V1 of 3 will not be 41.26? Can you be more specific? Looking at that? He wants greater than. Greater than or less than? Greater, because you imagine how it's accumulating, right? Imagine these cylinders as the volume accumulates. So let's try it. So I've written down over here, I've written down what the volume was and half the volume because I kind of stuck here. So what did we want? We wanted V1 of 3. I can't get there. Well, at least undo works, but I can't get down to the bottom. Nothing's working. Oh, no. There. I don't think there's any way I can do it here. Anyway, it'll be greater. I wanted to show you, but it will be greater than 41.26, but obviously less than 82.52. Okay, what about V2 of 4.5? So thinking about the volume accumulating from the bottom up, when we get to 4.5, is that going to be? That will be less than. You should say that's less. Okay, how about this? What if it was a rectangular region to start with, and we got the full volume? What about now? What about V2. So say we're going to rotate this whole thing now, and it's a perfect rectangle. And now I want to talk about V2 of 4.5. Is that equal to 1/2 of V2 of 6? Yes or no? I've got lots of yeses and a couple no's. Anyone want to say why it's no?
The radius is still larger above 4.5, so the volume of the cylinder is going to be larger.
Okay, yeah. So I have a symmetric region to start out with. But think about these shells in the first half. Their radii are smaller, right? So that's going to accumulate less than half the volume. When we get out here, the radii of the shells here is greater. So there's going to be more volume in this, more than half the volume in the outside half than there is in the inside half. So it's still, V2 of 4.5 is still going to be, even with the rectangular cross-section or region to start, it's still going to be less than half of all the volume. Do you see that reasoning? Do you understand that? If that whole rectangle was revolved the same way, and we're doing delta y intervals, right? So when you go halfway up in y, you're still going to get less than half the volume from 3 to 4.5 and more than half the volume from 4.5 to 6, because you have to imagine the cylinders you're using, which have a smaller radius, and the radius is getting larger and larger and larger. So you're going to get less than half the volume in the first half of the y values and more than half the volume in the second half of the y values. So V2 at the halfway point is going to be less than half of all the volume. Because the radius is smaller. Imagine these shells. These shells here have a smaller radius than these out here. So with a bigger radius, you're further away. A bigger radius, you're having more volume out there than closer to the axis of rotation. Okay. All right. Any more questions on volume? Sorry, my GC is not cooperating. Then it would be the same halfway. You'll have because all those cylinders have the same volume. Yep. He said if it's delta x in the second situation with the rectangular region, then V1 of 3 would equal half of the volume because all those cylinders have the same volume. The cylinders don't change in volume as you go across. I wish I could show you better, but hope you understand that. Okay. All right, so let's talk about the next thing here. Arclength. So we'll just talk briefly about arclength here. So arclength, so suppose that we have a stadium like this, and we want to know how much fence do we need around the stadium? How much fence do we need around the stadium? So if we could model that perimeter, say as a function, we want to know then what's the distance around that thing? What is the perimeter of that shape? And so that would tell us how much fence we would need. Okay, so we've talked about area, right? Area between the function and the x-axis. We've talked about making volumes by rotating a region and making an empty shell and filling that thing. So now this kind of another geometry application here is what is the length of a curve, the length of a function. And so you can think of it like, so here's a function from shown on the interval from 0 to 4. And so if we were to think of that as a string and stretch that out, how long would that purple string be? So what do you guess? How long is it going to be? So it's kind of showing you taking that purple string and stretching it out, and then we're going to put it on the x-axis. Whatever the length of it is when it's straight is the length of that purple curve. So it's going to have you guess, but I think this is kind of giving it away. So it's actually all the way. So the length of that purple weird-looking curve is actually 13 distance units. So if you were walking on that, you would be walking a distance of 13. Okay. So that's the idea here. Okay, so how are we going to do this? So here is a curve. There's the function up there. It's quadratic along with a cosine curve, okay, together. And so what we're going to do is we're going to break this thing up into intervals, and we're going to find those points on the function at those different intervals. And then I'm going to set a little animation going here. And I want you to talk about something while I'm going to take attendance. I want you to figure out if you were to label or use a symbols consistent with what we've been using, what would some different things be? And so there's actually 4 things I want you to talk about. So let me number them here. So just like always, we have x increasing, right? X increasing through intervals. And then we want to focus on what's happening in the current interval, all right? So what's happening in the current interval? So I'll just let you watch it here for a second, but then I'll pause it. Maybe this is a good place to pause here. There we go. Okay, so the first thing I want to talk about is what I've marked down here, number 1 in the circle. Okay, second thing is this right here. This is in the current interval. Okay, that's number 2. All right, and then that's number 3. And then this is number 4. Okay, so what do all those things mean? Or if we were to symbolize those things, consistent with what we've been saying so far, what symbols would you put on these different things that I've highlighted there? 1, 2, 3, and 4. Okay? How do we do? So number 1, what's represented by number 1?
Delta x.
Right, we start off with delta x intervals, just like we've done all along, right? So it's delta x. Each interval has a width of delta x. Is that what you said?
Yep.
And then we think about x increasing through these delta x intervals, and so we're always at some point in the current interval. So I paused life here, and we were looking at this situation, this interval here from something like, I don't know, like that's about 1.2 something. Oops. So about 1.2, and the end of that interval is something like, here's the current interval right here. And so what about number 2? That's our differential, dx. Dx what? Dx increases through the current interval, right? It's at the start of the interval, dx equals 0. And at the end of the interval, dx equals delta x. It varies. Dx is a variable in the current interval. It varies from 0 to delta x. Okay? And so right now it's almost done with this interval, right? So we paused life here. So number 2 is dx. That's our differential. That's a variable. Okay, what is number 3? Right, it's the corresponding change in y. Corresponding change in y. Okay, it's the corresponding change in y for dx. Okay? So I'm going to keep taking attendance now. I'm going to ask you a different question, and then we'll get to 4 later. What does dy equal? How are we going to? So we're going to need to get dy. We're going to need to get dy in this process of coming up with arc length. So, what does dy equal? Talk about it. Dy equals mdx. Okay, what's m? So up till now, we've had a context, right? We've had volume or temperature or weight or something, and we said that was the rate of change, right? The rate of change of our quantity with respect to x. Okay? But now this is just geometry now. This is just we're lying a string on the table, or we're building a fence, or this is the top of a wall, and we want to know how long this is. Okay? So we don't have like a quantity like time or weight or something like that. So what is m in this case? What is m in now? Yeah, so what about the tangent? What about the tangent? Yeah, the rate of change is represented geometrically by slope. So I heard someone say. Or what? dy dx. Okay, so it's the rate of change represented visually is the slope of that line. Okay, not the inclination. I can mess with the inclination all day by changing the axes, and it's the same rate of change. Okay, so really it's the rate of change represented visually is the slope. Okay, so what is the slope from your Calc 1? Okay? But if I need, so what do I need? I need the slope or the rate of change at all these different points, these starting points of each interval. Where am I going to get that from? Derivative. It's a derivative, right? The derivative. So it's the what? It's the rate of change of, if this is function f, it is. This is the function f. That m, when we're going to get dy by doing m dx. And that m is the slope or the rate of change or the derivative of our function f. And so that's our rate function. That's our rate function for f. But specifically, at what x value of the interval? Right? So notice that, so look at this interval here. We only care about the rate of change right there. And then for that whole interval, we're going to just stay at that constant rate in that whole interval. See that? The same rate that was here at the beginning. So we really want the rate at, remembers, at the left side of the interval. So in the current interval, that m that we need is going to be the rate of f taken at the starting point of the interval, the left side of the interval. So that dy is equal to r sub f of left x. Times, so that's m dx. Okay, what about number 4? What is that? So this is now finally getting to what we wanted in the first place. What was our whole goal in the first place here? To get, not slope, arc length, right? Arc length. So the length of that hypotenuse It doesn't seem like it, but when things get small, the length of that hypotenuse is going to be trying to be like the length of the curve over that interval. Okay, so where's a better example? So maybe in this, if you look in this interval here, you can see a little better. The second interval here. If you look in the second interval, do you see how the length of that red hypotenuse is kind of trying to be like the length of the curve in that interval? See that? Okay, so when we have these quick turns and quick twists and big intervals, you can't see it as well, right? But that second interval kind of shows it, that the length of that red is pretending to be the length of the blue curve in that interval. So we're going to use the symbol S for arc length. So if S is going to be our symbol for arc length, or our function name for arc length, then what would we call that length right there? We got dx, a little change in x, the corresponding change in y, and a little bit of arc length would be ds. So we've got everything we need to figure out. And so if we want to find an arc length, accumulation of arc length function, what do we need? What's the key? We want the total accumulation of arc length starting from some x value of a function. Then what's going to be the key thing we're looking for? The rate of change function, right? If we want the accumulation of arc length, we need the rate of change function. So this triangle now has everything we need to build the rate of change function. The rate of change function is ds dx. Or we know that ds is going to equal the rate of change of arc length dx. ds equals m, right? So it's just like dy equals m dx. But now the y we're interested in is not the y coordinate on the graph. That's important. But the quote y we want now is arc length, s. So ds equals r sub s dx. So how are we going to get that? Well, we look at this relationship. What relationship do we have between dx, dy, and ds? What relationship do we have that we can? It's a right triangle. It's a right triangle. So we can use the Pythagorean Theorem on that right triangle, since this is dy and dx are at right angles to one another. So I'll just show you in the book, rather than write it all out for time's sake, I'll just show you it's in the book. So here's what we said, right? So here's what we said. dx is how far we've made it in the current interval. dy is the corresponding change in y, and that equals m dx, and our m is the derivative at the starting value of the interval, dx, and then the approximating little arc length is ds. So we can just use Pythagorean Theorem, and ds squared equals dx squared plus dy squared. That's easy, right? Solve for s, solve for ds using square root. For dy, we plug in our m dx. We can factor out dx squared. And then the square root of dx squared is just dx. So looking at this right here, this tells us exactly what the rate of change of arc length is. What's the rate of change? This thing right here, the square root part, right? Because ds equals rate times dx. That should be very familiar. So we've got it. So what is our arc length function? S of x equals. So an alternate notation that the book starts using is two arguments. So you're going to start seeing this now, and it means the same thing as this, but now we're just also specifying that starting value a. So this is not a variable, right? This is not a variable. This is our independent variable, and this is just a parameter is where we're going to start, a, okay? So can you write, you should be able to write it, write out what this function would be. Okay, so what would the function be? Can you do it? Accumulation of arc length starting at A up to X. Accumulation of arc length starting at A up to X. If you're following what we've done so far this semester, you should be able to write out what that is. Okay, volunteer. Anyone think they got it? Is that a hand? No. Somebody new. Yes, sir. Integral from A to X. Oh, so we forgot to make things small. What does r sub f of left x become when the intervals get really small?
RF of x.
Just imagine a zillion little intervals now. So just looking at the rate at the left side of every interval, when the intervals get super small, it's just like looking at every rate, right? So what's that?
Exact rate of change.
Yeah, just r sub f of x, right? So,
Squared.
yep. I was just checking you guys. Accumulated arc length, right? Accumulated arc length. This is the rate of change of arc length. We're starting at A and X, and there's our arc length function.